Welcome back to another metrology and measurements session. Now we are going to move to the last unit of this metrology and measurement system. The topic of the last unit is measurement of power, flow and temperature. Measurement of power, flow and temperature.
This is the syllabus for the measurement of power, flow and temperature. Okay, in this course we are going to discuss about the force, torque and power, then mechanical type of force and pneumatic type and hydraulic and electrical type of power, flow and force and torque. In flow measurement, we are going to discuss about the venturimeter, orifice meter, rotameter, pitot tube, etc. So these are the measurements already we studied in the fluid mechanics and machinery, and we practically use this type of measurement in this fluid mechanics and machinery. And then temperature, how we are going to find out the temperature measurement with the help of the bimetallic strip, thermocouples, electrical resistance thermometer, reliability and calibration, readability and reliability. These are things we are going to discuss in this last course or last unit of this measurement of power, flow and temperature. Okay, after the completion of this last course, we can able to explain the measuring instruments to measure the power, flow and temperature. We can able to explain the measurement of power, flow and temperature.
In this measurement of power, flow and temperature, we are going to discuss about the measurement of force. Here we are going to discuss about what is meant by force, how we are going to measure with the help of the force, and what are the methods we are going to follow to find out the measurement of force. Here, first, we should know what is meant by force. Here, force is nothing but it is a basic engineering parameter. Force is a basic engineering parameter. This measurement, force measurement, is important in many engineering applications, such as weighing of an object, dynamics of vehicles, vibration studies, study of the behavior of materials under different types of loads. Okay. So, for this purpose, we are going to use this force measurement. Okay, now there are different measurement of which can be done in many ways is direct methods and indirect methods. Direct methods and indirect methods. Okay, first we should know about what is meant by direct method and what is meant by indirect method. Direct method means it involves a direct comparison with a known gravitational force on a standard mass. So, for example, we are using by balance. By balancing, we can get the measurement of force with the help of this direct method. Now, what is my indirect method? It involves measurement of effect of force on a body, such as acceleration of a body of known mass subjected to force. So, this is indirect method. Now, in direct method and indirect method, different systems we are following to find out the measurement of force. In this indirect methods, we are using equal arm balance, unequal arm balance, multiple lever system, pendulum scale. Likewise, for indirect methods, accelerometers, electromagnetic balance, load cell, hydraulic load cell, pneumatic load cell, and strain gauge load cell. First, we are going to see about equal arm balance. Equal arm balance. This equal arm balance normally we saw in grocery shop or vegetable shop. This equal arm balance is the most simple force measuring system. The basic principle operation is based on moment comparison. Here, there are two details like A and B, then C, then there's a D. Here there's a beam which connects the detail A and detail B, and there's a structure support which is to give the support for the beam, and there's a pointer and scale for marking the weight or weighing the weight, and that's a sample pad and a weight pad. This system consists of a beam. There's a beam which is pivoted on a knife edge fulcrum placed exactly at the center of the beam. Exactly at the center of the beam. When an unknown force is applied at one end of the beam, when we are applying the unknown force on it here, the mass of the other end of the beam balances the unknown force. The mass of the other end of the beam balances the unknown force. The pointer is attached to the center of the beam, and equilibrium condition is indicated by a pointer when it is absolutely perpendicular. So this type of measuring system is used in many places such as grocery shops, jeweler mart. Then likewise, the digital measuring devices replace this type of measuring device in now recent days. Then next one is unequal arm balance. Unequal arm balance. This unequal arm balance is that we saw in a coconut weighing shop. Okay, the major disadvantage of equal arm balance is that it requires a set of weight which is at least as heavy as the maximum weight to be measured. So in the previous equal arm balance, we need the sample weights to get the original weight of the unknown weight material. But in this unequal arm balance, it is used to measure the heavier weight with the help of lighter weights. It uses two arms, out of which one is called as load arm and another one is power arm. One is called as load arm and another one is power arm. Load arm is used to apply the load to be measured, while the power arm is to apply counter. When we apply the load on this, here we are applying the load on this pan, which is called as a load arm, and the other one is a power arm, which is used to apply the counter weights to balance in equilibrium. The balance can be specified in two ways. One is mechanical, in terms of mechanical advantage, which we can calculate load by power, and the other one in terms of multiplication ratio, which is defined as M is equal to power arm by load arm. So the distance between Q and G divided by distance between Q and P, which is called as L1 divided by L2. So this is the formula to get the values of the unknown equal arm balance. And the next one is multiple lever system. Multiple lever system. In this multiple lever system, it is used for the measurement of larger weights when compared to equal and unequal arm balance. Comparing to the equal and unequal arm balance, we can measure the larger weights on this multiple lever system. The measurement of large weight W can be done by using two smaller weights, WP and WS, where WP is the weight of the poise and WS is weight of the pan. The initial balance can be maintained by an adjustable counterpoise. The initial weight is maintained by the balance of the adjustable counterpoise. The poise weight WP is set to 0 of a beam scale before the unknown load W is applied to a platform, and the counterpoise is adjusted to be obtain initial 0 balance. The weight W on the platform can be replaced by two arbitrary weights, W1 and W2. So here the weight we can, with the help of the poise weight and the arbitrary weights, we can find out the original pan weight which we are applied on the pan to get the unknown weight of the load. So the next one is pendulum scale. Next one is pendulum scale. In here, there's a support tape. There's a support tape and a scale frame sector. There are two sectors and it is pivoted. And there's a weight and the counterweight. And there's a rack and pinion arrangement to move up and down on this section. And there's a weight scale with a pointer. And there's a load rod which pulls up and down. So these are the pendulum scale parts. It uses the principle of the multiple leverage system. The input is a direct force or a force proportional to weight. The input is transmitted from a suitable agency and applied to the load rod. And it is applied to the load rod. As the load is applied, the sectors rotate about a pivot, moving the counterweights. This movement increases the counterweight's effective moment until the load and balance moments are equalized. The motion of the equalizer bar is converted into indicator movement by a rack and pinion arrangement. So this is the working of an pendulum scale. Now we are moving to the indirect methods to find out the force measurement. First one is accelerometers. A force will make a body to accelerate. By measuring the acceleration, the force may be determined from the equation F is equal to ma. So m is nothing but it is the mass of the body. To measure the acceleration, accelerometers are used. To find out the acceleration, we are using accelerometers. Then the next one is hydraulic load cell. So here we are seeing the cross-sectional view of the hydraulic load cell. Here there is a hydraulic load cell arrangement. Here there's a platform with piston and it is a packing seal is there. And here there's a stud or nut and there's a diaphragm below the section, and there's a pressure or force applied, pressure gauge which indicates the pressure or force which is applied, and there's a liquid or oil which moves on the pipeline. So this is the schematic arrangement of the hydraulic load cell. Here the piston is placed on a thin elastic diaphragm. Here the piston is placed on the thin elastic diaphragm. or bridge ring made of steel. The piston does not actually come in contact with the cylinder wall. Mechanical stops are used to prevent the overstrain of the diaphragm when the load exceeds the certain limit. The load cell is completely filled with oil. When the load is applied to the piston, the movement of piston and diaphragm arrangement will result from the increase in pressure in oil pressure, which in turn produce the change in pressure on board-on tube pressure gauge connected with the load cells. So the major limitation of this type of load cell is need for minimization of friction between conventional piston and cylinder arrangement, and also requirement of packing and seal required to avoid the leakage of the oil. So these parameters are unpredictable, so it is very difficult to obtain. Next one is pneumatic load cell. This figure shows the cross-sectional view for the pneumatic load cell. So this is the pneumatic load cell. Here, this is the cross-sectional view for the pneumatic load cell. Here, the diaphragm of this type of load cell is made of flexible material. In this pneumatic load cell, there's a pneumatic load cell. In this pneumatic load cell, there's a load which is applied on above the diaphragm, and there's a nozzle is there, and there's an air supply, air which is over the entire tank, and here there's a supply which is gives inside for the air, and there's a pressure gauge which indicates the pressure. So here the load cell is designed to automatically regulate the balancing pressure. Air pressure is supplied to one side of the diaphragm and it is escaped through the nozzle placed at the bottom of the load cell. A pressure gauge is connected with the load cell arrangement to measure the pressure inside the load cell chamber. The diaphragm deflects when the load is placed on the load plate. The deflection of diaphragm affects the airflow through the nozzle as well as the pressure inside the chamber. The variation in pressure is measured by the pressure gauge attached with the arrangement. Okay, the next one is coil springs. In this coil spring, this is the arrangement of the coil spring. There's a hanger which is used to hang the coil spring, and there's a pointer which shows the output of the load, and there's a calibrated scale which is in Newton, and there's a spring which is pulled down by object, and object which is placed over the spring. Okay, here a spring balance is a device used for the direct measurement of force by using coil deflection spring. It consists of a spring fixed at one end and the load is applied at the other end. The displacement at the free end due to applied force is shown by pointer by moving on a scale. The deflection of the spring when a force is applied at the free end is given by the equation 8F d cube n divided by GD power 4. With the help of this equation, it is clearly that the deflection is linear function of force and it can be directly used as measure of force. Next one is proving rings. In this proving rings, there's a proving ring is there, and there's a vibrating reed and the micrometer wheel is there, and the scale arrangement is there to find out the exact dimensions of the force or measurements of the force. Proving rings or steel rings used for the calibration of the material testing machines in situations where dead weight standards cannot be used due to their bulkiness. The proving ring is a circular ring of particular length. It may support tensile or compressive force across its diameter. here the deflection of the ring is measured using a precision micrometer. To get precise measurements, one edge of the micrometer is mounted on a vibrating reed, which is plugged to obtain a vibratory motion. The micrometer contact is then moved forward until a noticeable damping of the vibration is observed. Maximum deflection is typically in the order of 1% of the outside diameter of the ring. So proving rings are normally used for the force measurement within the range of 2 kilonewton to 2 meganewton. Okay, here this is the schematic arrangement of the board-on tube pressure gauge. So in this board-on tube pressure gauge, there's a socket is there, and bellows board-on tube is there. There's a scale arrangement and tip of the board-on tube, adjustable link of the board-on tube, and segment lever of the board-on tube. There's a pivot which is pivoted, the entire pinion arrangement, and pinion and spring arrangement, and the pointer. So here in this board-on tube pressure cup, it is the simplest tube which will expand when it is exposed to pressure. So this expansion is the measure of pressure. One end called tip of the tube is sealed, and it is also called as a free end. It is attached by a light link work to a mechanism which operates the pointer. The other end of the tube is fixed to a socket where the pressure to be measured is applied. The internal pressure tends to change the section of the tube from the oval to circular, and it tends to straighten out the tube. Here there's a video. Now we are going to see the board-on tube pressure gauge. Here this is a board-on tube pressure gauge. This board-on tube pressure gauge which shows the pressure which is applied on the particular element. Here now we are seeing that we are going to see in this board-on tube pressure there is a working principle, construction, a working, and advantages and disadvantages. So here, first one is working principle. How the board-on tube pressure gauge works. When the liquid or fluid which is moved inside, it gives some creates some pressure on this tube, so it moves upwards. This is called as a C-type board-on tube, and the pressure which is created on here because it is sealed. We are using here the phosphorus steel and anything. So here there's a seal with the linkage with the pointer, and with the pressure of the fluid which is here, it moves over the entire board-on tube. Now working. When the fluid moves upwards, it gives the pressure on the entire C-type board-on. When it is down, it moves downwards. There's a segmental lever and just a link is there, which is connected with the sealed end, and there's a rack and pinion, and there's a pointer which is connected with the rack or pinion, and when it is moved, it automatically shows the pressure of the entire fluid given on the C-type board-on pressure tube. So it can varies when here there's a siphon tube is there. When the fluid moves inward inside the siphon tube, it flows the entire siphon tube to upwards. So here we can find out the fluid distance with the help of this. Here we can see the fluid which moves inside. Here the pressure which changes. So C-type board-on tube and helical type board-on tube and spiral type board-on tubes are there. So what are the advantages? This board-on tube pressure gauge gives accurate results. Cost of a board-on tube pressure gauge is very low. And board-on tube are simple in construction. It can be modified to give electrical outputs. is safe even for high pressure measurement, and accuracy is high especially at high pressures. What are the disadvantages? So they respond slowly to changes in pressure, and they are subject to hysteresis, sensitive to shock and vibrations. Amplification is a must as the displacement of the free end of the boron tube is low, and it cannot be used for precision measurement. Okay, and the next one is Bellows tube pressure gauge. Next one is Bellows tube pressure gauge. Here, the figure shows the Bellows tube pressure gauge. Here, there's a construction of pressure connection and case, bellows, spring, connecting link, and sector, pinion, and hairspring and scale. Okay, here now see the Bellows tube pressure gauge. So this given consists of the following parts. What are the following parts? Inlet A, where the unknown pressure is applied, and bellows made of brass or phosphor bronze. There's a spring arrangement, and there's a connecting link, and sector and gear arrangement, pointer needle, graduator scale calibrated in terms of pressure, and outer case. The bellows are in the shape of annular ring which are welded both internally and externally. The bellows contract or expand actually depending on the incoming pressures. The expansion of the bellows are restricted by the spring and thereby preventing the full expansion of the bellows. The mechanism will extend the life of the bellows and protects it. A bellows opening should be hermetically sealed such that there is no leakage of pressure. Now let us see the operating principle of the bellows gauge. The unknown pressure to be measured is applied at the inlet A. When the applied pressure is low or high, the bellows is squeezed or expand. This moves the link up and down, which is connected to the sector arrangement. The sector arrangement will now react to the movement of the link, and the pointer moves the over graduator scale. The readings on the graduator scale indicates the pressure value. When the pressure is removed from the case, then the link should come back to its original position. Let the applied pressure be P1, the atmospheric pressure of the bellows be P2. Case 1. When P1 is less than P2, the bellows will squeeze or contract. When the bellows squeeze, the connecting link is moved up. This pushes the sector down and the pointer moves over the graduator scale. When P1 is greater than P2, the bellows tries to expand. When the bellows are expanded, the connecting link is moved down. This pushes the sector arrangement up and the pointer moves over the graduator scale. Bellows gauge can also be used as an electrical switch. Bellows gauge is connected to any electrical circuit. When the inlet A is applied with low pressure, the bellows starts squeezing and thereby disconnecting the contact with the circuit. And the next one is electronic weighing system. In this electronic weighing system, this is the weighing system normally used in nowadays in groceries or any vegetable shops or any jewelry malls, etc. So it is a fully an automated electronic system. Here the system comprises the basic load cell, suitable signal conditioners, and output recorders, indicators giving both analog digital output for further processing. The signal from the load cells are added and amplified to give an output of 0 volt to 5 volt or 4 to 20 milliampere for process instrumentation. It is further converted into a digital format with an analog to digital converter so that the output can be indicated or printed out in a digital format or used for processing. The electronic weighing system can be designed to integrate with computer system with suitable software to include all functions such as totalizing, averaging, counting, and processing or any other such control operation. And next one is press detector. It is called as radial load cells. Is basically a magnetoelastic type force transducer. In this type of transducer, the permeability of a magnetic material is altered by the mechanical stress which is developed. The main application of this press detector is ideal for applications on a wide range of processing machinery in the steel rolling mills, plastic sheet rolling industry, printing textiles and other industry. It is also used in platform weighing, mobile scales and batch weighing systems, etc. So by this, we can wind up this session. Thank you.